Okay, so we're going to look at two things. We're going to look at two ways to calculate the moment of a force. And then we're going to look at how we put that information onto a stress diagram for a beam. It's more important that we look at the two ways to calculate the moment of a force. The stress diagram is a very simple, straightforward way of just showing that on a graph or a chart pictorially. So if we don't get around to that, that's not important. We can look at that next week. We'll look at what a moment is, and we'll look at the conventions around using these two methods for finding the moment of a force. And as you get more complicated with the moment diagrams we look at, it's important to stick to the conventions, whichever way you choose to use it. So it could be your choice as to which way you use to calculate the moment. Whichever way you choose, make sure you stick to those conventions. So let's have a look at a problem. Here is a beam. So there's already some conventions on here. First of all, we use this triangle to mean that's a fixed point on the beam. If I were to use a circle, and if I use a circle on here, it's going to do something weird on the board, but just for a minute, if I use a little circle on there, that means it's like a roller, so the beam is allowed to move backwards and forwards around that point. In other words, there's going to be no stresses laterally. We don't have to consider that, only stresses in the beam up and down. So I suppose that when I was sketching this out, I should really have made one of these a circle here, because we're not going to consider any forces on the beam in this direction, only in the vertical sense. So we label our positions that this beam is being supported. So those are the two supports. We label them A and B. It doesn't have to be A and B, but we label them. And then we put on any forces that are acting. So there's a point force acting here, straight down, of 20 newtons, and another point force acting down of 10 newtons. In this particular example, we are ignoring the weight of the beam. We'll see what we have to do about that in another example. Now, a little talk about moments before we continue on. If I take a force acting on something on that point there, then the force 10 newtons, that's the force that I apply, 10 newton force on a point. However, if I decide that on that point I'm going to exert a force by using a lever of some sort, we all know just by trial and error that if I want to exert a bigger force, I can use a turning force like this to exert a bigger effort at this point, or a bigger load at this point. I have an effort here that I'm applying. Okay? And I'm sure you've come across this idea before, this sort of machine idea. And the longer the lever, the more effective the thing is. So the effect of the force is to do with not only the size of the force, but also how far we are away from a pivot point. So moments are to do with when we're trying to allow a force to turn something around the pivot. As soon as we start to do that, as soon as we start to turn forces round pivots, either clockwise or anti-clockwise, in other words, the force is not acting at the pivot point like it was here, then we calculate something called the moment of the force. And that equals the size of the force times the distance from the pivot. So the moment is given by the moment of a force is the force times the perpendicular distance from the pivot. That's a definition of the moment of a force. It's the force times the perpendicular distance from the pivot. So if that's the distance d, and that's the force F, and this is the pivot here, pivot, then the moment of the force is the force times the distance. So m is the moment, F is the force, and d is the distance. So you could add that to your formula sheet if you want. So what do I mean about this perpendicular distance here? Well, if this force is acting straight down, then this is the perpendicular distance. In other words, there's a right angle between the direction of the force and the distance I'm measuring from the pivot. So that's a perpendicular distance. If this force was not acting at right angles, but it was acting like that, then what I would have to do is start to use geometry. I would continue this line down here like this, and work out this distance, which is the perpendicular distance from the pivot. Or if the force is acting in this direction, I would continue this line back here and again work out the perpendicular distance. If I knew angles that were involved, I think you can see SOHCAHTOA would start to come into play, trigonometry in other words, and that's the sort of thing we'll be talking about in the engineering maths as a technique. So that might come up in a maths exam, but it won't come up in this. We're only going to be considering, luckily for you, perpendicular distances all the time. So if I give you a distance, it's the perpendicular distance. But when we're stating and defining moments, then we need to state the perpendicular distance because of what I was just saying. We've got to find out what that is by making a right angle triangle. So it's not too complicated, but we're not going to worry too much about that. So what do we do to work out what's going on in here? What I'm after is two forces called reaction forces. So R stands for a reaction force. What's the reaction force acting at B? What's the force that I would feel if I was to take this support away here and hold that end? What force would I be feeling to hold that up? And equally, there's another reaction force at A. So if I were to take this support away, what would be the reaction force required to hold that up if you were holding it? And I think you can see that it's likely that this reaction force here is going to be bigger than the reaction force at A, because these load forces are further to the right, aren't they? Further towards B. So if you were holding this end, you're likely to be feeling more force, aren't you? So what we're going to do is come up with a way of finding out what reaction force at B is and the reaction force at A is. Two methods, as I've said, and also a way of checking that we've done it correctly. Because if you're doing this at work, somebody said to you, calculate this for me, I would want to feel confident that was right before I went to my boss and said, this is the value. This is the size of the beam you need to buy to hold that force. So let's have a look. So the first method, what we do is we assume the pivot acts at one end. So we're going to assume it's pivoted at A, say, and then find the reaction force at B. What is this force here? So we replace this support with a force acting upwards and find out what the size of that force is. And what we have in mind is that if this thing is not moving, then whatever the moment is going around this way due to that force is, And whatever this moment is, due to this force going this way, both of them trying to turn it clockwise, are being counteracted by an anti-clockwise moment going that way, which equals this force times that distance. And that's the idea. So the first thing we do is we say pivot at A. So we're going to assume the pivot's at A. And then we're going to find anti-clockwise moments. ACM for anti-clockwise moments. Equal. And then what we do is we look for all the forces that are trying to turn round anti-clockwise, which is this force, the 20 Newton force, and this force, the 10 Newton force. Ignoring the mass of the pivot for now. So those are the only two forces acting. We're going anti-clockwise first, aren't we? So which ones are going anti-clockwise? That one, which is the reaction force at B. So what are the anti-clockwise moments? The reaction force at B times that distance, the full length of the pivot, which is 5 meters. So that's going to equal the reaction force at B times 5. Which, if I want to write it algebraically, thinking about this morning, I'd put the number first and then the letter RB for reaction force at B. And then I find the clockwise moments. What are the moments trying to pull it round clockwise? And there's two of them. There's the moment due to this force, which is 20 newtons times that distance, and 10 newtons times that distance. So this is 1, that's 1, and so if the whole thing is 5, then that must be 3, and that must be 4 meters. So 20 newtons times 3 meters is 1. And I'd put that in a bracket for that moment, plus 10 newtons times 4. Remember what I was saying about convention. If you set it out like this, if I've got lots of forces and lots of distances that aren't exactly whole numbers, I don't want to be trying doing things in my head, so I'm just pointing out to you the conventions that are going to help you to set this out. Which equals 20 times 3 is 60, 10 times 4 is 40, 100 Newton meters. I didn't mention the unit for forces. It's newtons times meters because it's force times distance. So 100 Newton meters is the clockwise moment. Now, at balance, assuming that this thing is not moving, I say anti-clockwise moments must be balanced by clockwise moments. So I say anti-clockwise moments equals clockwise moments. That's a statement. At balance. So if this thing is static, it's not moving, and all the stuff that we're doing in this part on supported beams will assume it's a static situation, nothing's moving. So then that means anti-clockwise moments equals clockwise moments. So we can say that 5RB equals 100. And that's just a straight equation. So what's RB? Divide both sides by 5. RB equals 20 newtons. That's the reaction force at B. So to recap, what have we done? we assume there's a pivot at one end. It's up to you which end you picked, A or B, it doesn't matter. If it's pivoted at A, the anticlockwise moments are given by this, the reaction force at B times the distance from A, and then the clockwise moments are the moments due to the two forces that are trying to pull it round clockwise. We work out what that is, put anticlockwise moments equal clockwise moments at balance. That gives us a little equation that we can solve to find the reaction force at B. That's the method. What do you think we do to find a reaction force at A? Right, we assume the pivot's the other end. So now we go pivot B and work through the same method. So I'll just pause this and let you do that. Work out what the reaction force is at A. Okay, clockwise moments is 5 times the reaction force at A. Anticlockwise moments, now the 20 Newton force is acting 2 meters away from B. Whoops. So 20 newtons times that distance 2 plus 10 newtons times that distance 1. So I put them in. 20 times 2 plus 10 times 1 comes to 50. Put anticlockwise moments equals clockwise moments, and the action force is 10 newtons. Okay? Now, I want to check that's right. Let's look back. I think now that the reaction force at B is 20 newtons, and the reaction force at A is 10 newtons. So I can put those on my diagram. Now I think I'm right. To check, I apply another law of physics. And it's again to do with balance. If nothing's moving here, the total forces acting downwards surely must equal the total forces acting upwards. Otherwise, it would either be moving down or moving up. So I add together all the forces acting downwards, 30 newtons. That should equal all the forces acting upwards. 10 plus 20 is 30 newtons. So that helps me to think I must be right. So my check is to say total up force must equal total down force. That's my check. So I add up all the up forces. And I add up all the down forces. And if they're the same, I conclude there's a fair chance I've not made a mistake. There is an argument to say once I've found the reaction force at A, all I've got to do is subtract that from the total downward force, and I've got the reaction force at B. I don't need to go through all that. But I would rather use this as a check that I've done it right. Because if you've made an error in the first one, you're not going to find it. They'll both be wrong. So the second method, pretty well the same. You're finding the clockwise and anti-clockwise moments, but it's a convention about the way you set it out. So let's have a look at this second method. Same problem. And this is the convention here. So I'll just pause while you write this down, and then we'll have a look and explain it. This symbol here, you might recognize as capital sigma, this one here. Looks like this, and used in statistics to mean the sum of, and in this case that means exactly that, the sum of the moments. So sum of the moments about A equals 0. And there's an arrow going around here with a positive sign on it. So let's look at this. What it's saying is, in words, a sum of the moments, so that symbol there, sum of the moments M, about A. So that subscript means I'm taking moments about A, sum of the moments about A, equals 0, taking all moments acting in the anticlockwise direction as positive. So that means, by implication, that any moments acting round clockwise must be negative. So that's the convention we're going to use. So all we do now is write down our moments in one equation. I take all the moments acting clockwise as negative, because my convention is anticlockwise, it's positive, and my moments due to the reaction force to be positive. So what I do is I write this. The sum of the moments about A are, I need to see this at the same time, going positive first, so reaction force at B times 5 times the reaction force at B, that's positive, minus 20 times 3 minus 10 times 4 equals 0. The sum of the moments about A equals 0, taking anticlockwise as positive and clockwise as negative. So that's the anticlockwise, effectively, going positive, and these are both going clockwise, so they're taken as negative. You don't need to put those arrows in, but I'm just there to help you see it. So now I'll say 5RB minus 60 minus 40 equals 0. Minus 60 minus 40 is minus 100 equals 0. Add 100 to both sides, equals 100. Divide both sides by 5, 20. Same answer, but set out differently. When I was taught this many, many years ago, I was taught the first method. This second method I quite like, actually, the more I use it. The convention seems to be neater, and it's a bit less to write down. But, you know, they're both equally valid. I wouldn't like to choose between one or the other. Why is it true that they must equal 0? And if it didn't equal 0, it would be unbalanced and it would be either turning clockwise or anti-clockwise, exactly. So that's the fact that they equal 0 is a consequence of it being a static situation. So they must all be balanced. So now what I do is I find the sum of the moments about B equal to 0, taking anti-clockwise as positive or clockwise as positive, up to you. So now, just to complete this, find the sum of the moments about B, taking anti-clockwise to be positive, equals 0. So just set that one up and work out the answer. So I'm sure you got that right. The same check to make sure you got the right answer. It's up to you which method you might want to try both ways for a couple of examples. We'll look at a few more in a second and then make your decision. I want to just show you for this particular example this shear force diagram I talked about, this force diagram to show the forces acting on the beam. So here is a sketch of it. We've got an axis and below it is the situation we're looking at, the one we've just been talking about here. So let's just shift this up a bit so I can see it. So this is a shear force diagram, it's called. So it just shows the forces that are acting on the beam. So it's just to show the forces that are acting on the beam. Let's look at this beam down here. Again, ignoring the mass of the beam, and that has consequences for this shear force diagram if we don't do that, as we'll see. But ignoring that, we first of all draw on here the reaction force acting at A, which is upwards 10 newtons. So we go up to 10 newtons on here. And then that force is the only one that's acting until we get to this point, when there's a 20 newton force acting downwards, ignoring the mass of the beam. So that means the force continues, and we can draw a sort of like a guideline here at that point. So what we say is a force of 10 newtons acts until we reach here. So at this point here, a 20 newton force acts down. So what I now do is come down 20 newtons to minus 10 newtons, which is this point here. And then that force is the only one that acts between this point on the beam and this point on the beam here. So it continues at that force of minus 10 newtons until you reach this point here. So minus 10 until we reach here. And then we get a down force of 10 newtons. So it goes down again to minus 20 and then continues at minus 20 until you reach the reaction force. Oops, gone too far. The reaction force at B, and then you go up 20 and you go up 20 and you should get back to the axis again. So that's your shear force diagram, showing the forces acting on the beam. 10 newtons up to this point, minus 10 that way, minus 20 and then back up. There's another example. You've got this in your booklet. Calculate the reaction forces and produce a shear force diagram for that beam. Notice in this example, correctly is drawn that circle at this point, meaning that's a roller, so there's no lateral stress being exerted on this. It's allowed to move right and left as it's required to do. So no stresses in the lateral direction, only in the vertical direction. So again, you can label these points A and B, as we did before, and then using one convention or the other, or both if you prefer, to see how they work. Find the reaction force at A and the reaction force at B. You've now got 3 point forces acting. Again, we're ignoring the mass of the beam. Use the total upward forces equals the total down to check you've done it correct, and then try and draw a shear force diagram at the end.